Hi, and welcome to API CAN Codes Unit 3, Data Science Practices. We'll start off with this lesson 3.1 on data visualization. We start with a warm-up demonstrating the power of visualization. In this first picture, you can have students try to count all the sevens. And in the second one, where we've modified some things about the way the data is visualized, students might notice it's actually a lot easier to accomplish that task. So we've presented the information in a slightly different way that makes it much more accessible. We're going to quickly recap Unit 2 before we continue to expand on this idea. So in Unit 2, we learned a lot about the computational foundations of data science. We used EduBlocks to request data from different APIs and some different code blocks to process that data in different ways, and saw generally that EduBlocks can be a pretty powerful programmatic tool for helping us through some of this analysis. In this unit, we're going to take that next step and go from data that we've analyzed in EduBlocks and create things like data visualizations out of this. So we want students to explore this page, why your brain craves infographics, on their own. Some potential questions that you could ask them are, what are some advantages to infographics? What problems can infographics help solve? And what makes infographics efficient? Next up, we have a video of the Stroop test. So students should try to go through this video reading the color of the word and not the word itself, which is more challenging than it sounds. Infographics are visual representations of information that are intended to present complex information quickly and clearly. We have a few examples of good data infographics over the next couple slides. First, the visualization of Napoleon's invasion of Russia, which is a little challenging to interpret, but effectively that sort of brown beigey line is the number of men in the campaign on the way out, headed to Moscow. The width of the black line is the number of men coming back in this army. And another thing that you can see is on the bottom, the temperature in degrees of this thermometer. It's not the Fahrenheit scale, which is a little bit confusing, but you can see like where the temperature drops at different points. And I think they do have a Celsius and Fahrenheit translation there as well. And what this really shows is the failure of this invasion because so many men were lost across the course of the advance and then even in the retreat. So some more examples. We've got here the daily routines of famous creative people, Hollywood hits and flops of 2023, and data breaches by data sensitivity. We highly recommend having students go through one or more of these examples, trying to think about what's effective about them and how they make sort of this information presented clearly to their audience. So a lot of different reasons why infographics can be helpful. And we're going to refresh students' memory of the DIKW model, where data becomes information. Information can be turned into knowledge, and knowledge can generate wisdom. Infographics are sort of in the information into knowledge stage of this DIKW model, and they help translate from raw data into something that's actually usable, actionable, intelligible. A few common types of infographics that we're going to go over. So first of all, on the largest scale, we have graphs, we have tables, we have flowcharts, we have maps. There are probably other infographic types that we don't include here, but these are kind of the big ones. If we go further into some common graphs, we might see bar charts. Those are going to be common. We might see pie charts. We might see line graphs. And we'll delve a little deeper into each of these examples. The first we're going to look at is a bar chart. A bar chart either uses vertical or horizontal bars to show discrete numerical comparisons across categories. So in this bar chart, you can see each pet is its own bar. And you could ask students how they would interpret this graph. Hopefully they'll point out that the y-axis acts as just a count here, and each of these bars represents a different category within this overall group. Some more common types of graphs are scatter plots, box plots, and histograms. The example we have here is a scatter plot showing a relationship between two variables. And here we have square footage on the x-axis, price in thousands for homes on the y-axis. Students probably will notice that as we go from left to right across this graph, the larger homes tend to be more expensive. So there is a positive relationship between those two. A few more common types of graphs. We've got bubble charts, we've got area charts, and we've got tree maps. These might be students might be a little less familiar with this, but you can talk about each of them. And we'd like students to go into this bubble chart and explore some of the data that's here. In their worksheet, they should answer, what does each axis represent? What are the 3 countries with the highest income in 2021? And to see this, they can look at that x-axis for GDP. And then we'd like students to change the indices and axes and examine the graph over time and see what insights they can draw from this changing graphic. So we also want to introduce students to the data visualization catalog. We hope that this is going to be helpful in this unit, but also in the final project when students are thinking about how to convey the data that they have from their API dataset. So students should open this link, the data visualization catalog, and see what's there. Students should be able to click on any of these graph options and more to learn more about what that particular kind of data visualization gets used for, what sorts of variables it tends to be very good at representing, and some sort of common ways to either recognize that or to use it. So using this website, students should answer the 3 following questions. When is a box and whisker plot used? When is a bar chart used? And when is a bubble chart used? Our goal here is really to make sure they know how to explore the site by clicking on the different graph options and seeing how these questions get answered within those pages. So for the next couple slides, we're going to pose a scenario, and students should choose the graph type that fits the situation best. For example, in this first slide, we say we want to visualize the frequencies of different car colors among all cars parked in a college parking lot. Some students might say a bar chart. Other students might say a pie chart. Both of those are actually pretty solid answers, and there may be more. What's important here is that in defending their choice to the class, students are thinking about what different visualization types get used for. In the next slide, we have a data analytics company wants to represent the relationship between the amount of funding a school district receives and the average GPA of students in this district. Probably the obvious choice here is a scatter plot because we have these 2 numeric variables that are related, but students might come up with a slightly different answer, especially if they're looking through the catalog. Finally, an app for a GPS tracking collar for pets wants to create a graphic to show the total numbers of steps taken by pets in various cities throughout the United States. This one is a little bit trickier because we do have this location element, so students probably want to choose a graphic that has some kind of map on it. One popular answer might be sort of a bubble chart that has bubbles of different sizes for different cities in the United States, so that location information is preserved, but we also have a sense for this number of steps. Numerical data can be misused, either intentionally or by error. A lot of the times this comes up in so-called graph crimes, which is a Twitter account as well. But you can usually see the following mistakes in graphs. Sometimes a portion of the y-axis is cut off, right? There's a break in one of the axes. The scale of the vertical axis can also be manipulated to make sort of differences look smaller than they really are or larger than they really are. We might selectively present only certain data points or time periods, and pie charts may have inaccurate proportions. There's also some other graphs that represent area to show differences, but often do it poorly, and we'll look at a couple examples of what this looks like. First, our first example is showing heights in different countries. The problem with this graph is really that as the people well, there's a couple problems, but as the people get taller, they also get wider. So if you look at, for example, the Netherlands character, he's just about 4 times the size of this gentleman from the Philippines, which doesn't really make any sense given that their heights are actually not all that different, right? They're different by, if you look at the graph, less than 25 centimeters on average. The other problem with this graph, and this is a little harder to catch immediately, but the y-axis scale begins at 1.5. So even though these men are depicted as standing on the ground, this is really only sort of the top, however many centimeters of each of them. So a way to fix this graph might be to, first of all, make sure that all the, like these are effectively bars, make sure that they are all the same width, and also make sure that this y-axis starts all the way down at 0 so you can really see that the difference is not quite as significant as what this graph makes it out to be. In the second graphic example, we have cost overruns of the Olympic Games for a bunch of different years. The main problem with this graph is that it changes the radius of the circle rather than the total area of the circle. What I mean by that is if you look at the 324% circle, it is like 4 times smaller than the 720% circle, even though that's really only about half the cost overrun. So a way to fix this might be to make the area of the circle vary based on cost overrun rather than letting the radius of the circle vary based on cost overrun. And if you look at the legend, you can see a really good sort of explanation for why this doesn't go so well, because the circles really get bigger at an exponential rate, not a linear one, and that doesn't quite make sense. Here's a pie chart with a mistake in it. Students will probably pretty quickly recognize that the percentages in this pie chart add up to well over 100%. And that doesn't really make sense for a pie chart, which is supposed to be showing how a whole population is divided up. A better way to do this might have been to, well, this one could actually be represented with a bar chart if these are 3 sort of separate categories that we'd like to represent side by side. It doesn't really make sense to have these 3 percentages in a single pie chart. And one of the last examples here, we've got the percent of people agreeing with this court. We have Democrats in one bar, Republicans and Independents in these other 2 bars. At first glance, this difference looks pretty significant, but again, we have a y-axis issue. This y-axis only goes from 50 to 64. So in fact, Republicans and Democrats, for example, only vary by 8 percentage points. Both are sort of majority agreeing with the court. So really this difference is not as significant as the graph makes it appear to be. We could do a better job by starting this y-axis down at 0 and rolling maybe even all the way up to 100 to show that this difference is much less significant than we're seeing here. Finally, a graph that doesn't really do anything wrong, but is almost completely inaccessible. And the reason I'll say that is because there is so much overlabeling on this diagram that it's effectively unreadable. What I like about this graph is the simplicity of sort of where you can and can't drink tap water. I think in some cases we may be blurring an entire country into one color, but generally it does function. There's so much text on the slide though that it is very distracting and actually hard to use. We want students to do an exit ticket today that helps them practice this skill. So we have average annual household income from the UK, and we'll let students answer this themselves, but one of the issues that we noticed is the piles of money do not increase as much as they should from 22,000 to 32,000 to 108,000. That 108,000 obviously should be much, much higher and is only slightly higher than the 32,000. So what they've done here is a fairly confusing way of representing money using this sort of area volume model, when in fact they probably should have just done a straight up bar chart with 3 different bars where the height directly corresponds to the amount of money. As always, thank you for watching these lesson videos, and thank you for teaching the API CAN code curriculum.